Greetings. In this video I am going to talk about some basic postulates in plane geometry. By plane we mean flat surface, and this could also be known as Euclidean geometry, named after the Greek geometer Euclid, who wrote the first geometry textbook, and we still have copies of that textbook today. So we're going to look at 8 postulates here. And these are the ground rules for how geometry works, sort of like rules for a sport. If you change one of the rules, then you change the sport. If you change one of the postulates, you potentially don't have something that's logically consistent, or you create an entirely new type of mathematics. And historically, that's what's happened to get some of the other geometries that we have, is a postulate was changed, and so you got a new geometry. So we're going to look at these. A few of them are going to sound kind of the same, and maybe we'll highlight a little bit of the differences. The first one is, through any 2 points, there is a unique line. So maybe you recognize that from an Algebra 1 class. You could plot 2 points and then connect the dots, and that was the line that you were trying to graph. The second one says, through any 3 non-collinear points, there is a unique plane. So after you've fixed 2 points on a line, pick a point out in space around it, and you will be able to pass a plane through that line and through that point, and so you uniquely identify a plane. If you change the position of the point, you would change the position of the plane. This third postulate we're going to look at may sound very much like the first postulate, but there's a slight difference. The third one says a line contains at least 2 points. This is a little different from the first one. The first one starts with says 2 points and then a line. This one says that a line contains at least 2 points. So you start with the line and you move to look at the points. But this says at least 2. So this is kind of the minimum value that's established. So a line has 2 points, but that's the minimum value, so you can have more points. And in fact, one of the ways that you might approach the undefined concept of a line is to say that it is an infinite string of points that are pulled tautly so that there's no slack in it. The fourth one is similar to the third one in the way that it reflects back to a previous postulate. This one says that a line contains at least 3 non-collinear points, and so that establishes a minimum of 3 points in your plane. The fifth one states that if 2 points of a line are connected in a plane, then the plane contains the entire line. So if you have a plane this way and you have a line that passes through it, then there could be a point of intersection between the line and the plane. But if you have a second point of the line that is coplanar, then you know the entire line is going to have to be there. The sixth postulate that I have here is that if 2 lines intersect, their intersection is exactly 1 point. So 2 lines pass in space. It's like the same as driving on a road and you come up to an intersection. There's 1 intersection there as 2 roads intersect. The seventh postulate that we have here is that if 2 planes intersect, then their intersection is a line. So as 2 planes come together, the part where they both meet, that is a line. And then lastly, the 8th postulate that I have today to talk about is the ruler postulate. And basically it says that a line or a segment, because it's a piece of line, can be put in 1-to-1 correspondence with the real numbers. So essentially you make a number line out of it. And then once you have this gauge of numbers on it, you can measure some distances on the line or the entire length of the segment if you need that. So these are basic ground rules. We're going to look at a theorem now, and that's the midpoint theorem. I'll add a definition up here for the, we want the definition of what a midpoint is before we do the midpoint theorem, and we can include at least one of these postulates in that proof. Alright, I have definition of midpoint on the board. It tells us that the midpoint of a segment is the point that is halfway between the endpoints of the segment. And then I also have the midpoint theorem on the board, and it says that if M is the midpoint of a segment, xy, then segment xm is congruent to segment ym. And we're going to prove that with a two-column proof. The first thing that I want to do, though, is I want to sketch what we want to prove. And you can sketch your own. Mine may not be the best sketch. You don't always want to believe everybody's sketches, because sometimes we may introduce some of our assumptions into the sketch and maybe argue for something that we shouldn't or isn't really present. Alright, so my sketch is very simple. It's a segment, x, y, and m is in the middle, and we hope to find that the segment xm is the same length as the segment my. And so, we're going to start with the if statement. You start with the m statement, and then your then statement should be the final statement in your two-column proof. Alright, so there's my first column. M is the midpoint of xy. I'm taking that directly from the theorem, and so we're going to state that as our given. Then we are going to state that segment xm and segment my are going to be equal in length or size. And we're pulling that from the definition of the midpoint. And then we could say something about, we could actually measure these. So we know that the midpoint is halfway between the two, so we're saying that these segments should be equal, but we could also make a statement about measurement as well, just to add some solidity to the statement. So we could say that the distance between xm and the distance between my is going to be measured the same through the ruler postulate. Some people may say that you need one or the other, maybe not both. I think it's better to have more information, more reasoning than less, so that you don't miss some piece of information that might be important. And then from this statement also, since m is halfway between and the measurements are the same, then we can say that they must be congruent. They have the same measure, but they're occupying different places in space, so that's definition of congruence. And at that point, we have this line, which was the then statement here, so we have completed this proof. Cheerful calculations.